Reservations in two-way slabs by means of yield lines. This video deals with the cases 26 to 30, and it's about a concrete slab who has two fixed ends and two simply supported ends opposite to each other. We will handle case 29 now, but cases 29 and 30 are special because the yield lines do not follow the rule of 30, 45, 60 degrees. The yield lines are corrected by the corner of the reservation. That gives you more realistic yield lines. So we have now case 29, which is a centric reservation, centric placed into the slab and attracting the yield lines, just to show how it can be calculated. So the angle of the yield line is not following the 30, 45, 60 rule. Because it's a two-way slab, B must be between A and 2A. The maximum size of the reservation, of course, B2 must be smaller than B and B1 smaller than A. The horizontal symmetry means, in fact, that D2 plus 2 times D4 must be equal to B, and D1 plus 2 times D3 must be equal to A. So that are the only conditions. And you can have now some examples of a rectangular reservation or a square or a rectangle reservation, horizontal or vertical. The work done by the external forces can now be calculated. For the orange parts, it's the rectangulars. So it means that, for instance, here you have D3 times D2. You have that 2 times. And this is D4 times D1. And you also have it 2 times. So the sum of the surface multiplied by the mean deflection, which is delta over 2, because it's a rectangular. We add to that the summation of the green parts of the triangles, and we have 4 corners, 4 identical corners, so that's the 4. And we have D4 times D3, and the mean deflection of triangle is delta over 3. So that's this. You see, it's much easier using attracting yield lines to calculate the maximum bending moment. We substitute or we change it to dimensionless units or dimensionless parameters, and we have this expression. The work done by the internal forces is the projection on this axis of the negative bending moment, m, multiplied by the angle, which is delta over d3. You also have this on this side. It's b, or m times b, multiplied by delta over d3. Then what's left are the 4 corners, and this yield line is projected to the north, so the length is d4, angle of rotation is d3, so d4 divided by d3, and the other yield line projected to this axis of rotation is d3 over d4. So, and we have that 4 times. We substitute or we change it in dimensionless parameters, and we have this expression. We make D equal to E. From that, you get M, and M is then following this expression. Bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. We have seen in the previous videos that the maximum bending moment without the reservation is equal to this formula. So we can now express this formula in a closed formulation. We see that here 1 min alpha 1 means that alpha must always be bigger, or alpha 1 must be smaller than 1. So then you have this, which is logic. The same happened for alpha min alpha 2. This is also logic. An example, when you have a reservation of, for instance, a slab 9 by, let's say, 6 meters, and you have a reservation it like that, situated in the center with a width of 0.5 times 6 and uh, a width, sorry, of 0.6 meters and a length of 3 meters. So it's quite a large reservation, but we will put it in this formula. We calculate the bearing capacity. You see it's 140. So it means by making a reservation like that in the slab, you do not touch the original bearing capacity. We can now put the bearing capacity on the y-axis and on the x-axis alpha, which is b over a, going from 1 to 2. And we can fix, for instance, the width of the reservation at 0.2 times a and vary the length of the reservation. And then you get different curves to see what is happening in this region. This is the region that we are interested in. The other is not that important, but when are we touching the bearing capacity? Let's say we have a slab of alpha 1.6, a reservation of a square in the middle of 0.2 by 0.2 times a gives you 104 as bearing capacity, which is this point here, because we are in this curve. When we make a reservation horizontal of 0.2 by 0.4, then we are here on the blue curve, and we have 99.1. And when we make the reservation bigger, we are at 95.3, which is this curve. So you will see you go from there to there. And it happens also with the other alphas. And at last, for alpha, alpha 2 equals 2.8, you have this. So this is a change of alpha 2 in the length of the reservation. And this is the change in bearing capacity. Now let's study it for alpha equals to 1.5 and in function of the smallest size of the reservation, and this in function of the other side. Then we have curves like this. You see again, this is the region that you are interested in. We will enlarge this region to this, and then you will see that in this area, all those combinations we should avoid. According to the size of the reservation, you could avoid all those elements. So by using these graphs or this formulation, you can decide what's the best place to put your reservation in the slab. We can now do the same for alpha equals 2. Again, we are interested in this portion of the graph. You can now enlarge this, and then you have here all the combinations that you should avoid when making a reservation of type 29. We can also look at it in a different way. We put everything in function of alpha 2, and with one width of the reservation fixed to 0.1, and for different values of alpha going from 1 to 2, then you have this type of, of, of functions. You can enlarge it in the zone which is interested. So this is this zone here. And now you have a clear view for different labs going from 1 to 2, alpha going from 1 to 2, and with a constant width of um, reservation equals to 1/10 of the smallest size of the slab, then you can choose alpha 2 to be sure that you do not have any loss in bearing capacity. So this is in fact the minimum or maximum value of alpha 2 that you may have. So this is the right zone. This is the zone that you have to avoid. We can now handle the same formula for a square hole in a square slab. So it means that D1 is equal to D2 and A1 is smaller than 0.6. We do that because otherwise when this reservation is too big for the slab, then the yield lines, extracting yield lines are not realistic because this must not coincide with this side, or this yield line must not coincide with this side, because otherwise you will have two yield lines on the same spot. So to be a little bit realistic, you will have, for instance, 0.2 times A as a safe distance from the side. That's why I put this alpha 1 smaller than 0.6. You can put it, you can substitute this in the previous formulas and you get this expression. We know M0 is equal to that. And because alpha is 1, alpha is 1 here. And then the bearing capacity is then only a function of alpha 1. And we put it in the graph. Then you see that for alpha 1 going from 0 to 0.6, the bearing capacity for the smallest size of the reservation is less than the original one, and if it's bigger, it's more. So first thing we notice is this here in the corner. When you calculate the bearing capacity of alpha 1 equals 0, it means it's the bearing capacity without the reservation. We got 97% instead of 100. It should be 100. We lose 3% because this is calculated with attracting yield lines, while the bending moment without the reservation is calculated with the 60, 30, 45 degree rule. So in M0, if you 100%, this angle is 60 degrees. So that's why you have here not 100 for both. Then we see that the maximum, or that the bearing capacity is 100% when alpha 1 is 0.308 and it's 93. The maximum here for alpha equals to 0.134. It means that the bearing capacity is smaller than 100 for alpha 1 between 0 and 0.308. So we can conclude that we should avoid making holes or reservations smaller than 1/3 of the slab dimension.